This text discusses the imports of various libraries and modules used for data processing, visualization, machine learning, and imbalanced data handling. Here is an overview of the main components imported in this code. 1. NumPy, imported as NP, a library for numerical operations in Python, particularly for working with arrays and matrices. 2. Pandas, imported as PD, a data manipulation library used for data analysis and handling tabular data structures such as dataframes and series. 3. TensorFlow, imported as TF, an open-source library used for machine learning and deep learning applications. 4. Matplotlib, PyPlot, imported as PLT, a data visualization library for creating static, animated, and interactive plots in Python. 5. Seaborn, imported as SNS, a data visualization library based on Matplotlib, providing a high-level interface for creating attractive and informative statistical graphics. 6. Sklearn. Scikit-learn is a machine learning library that offers simple and efficient tools for data mining and analysis. It includes a variety of supervised and unsupervised learning algorithms. The code also imports specific modules for tasks like dimensionality reduction, PCA, TSNE, classification, logistic regression, SVM, k-nearest neighbors, decision trees, random forest, and handling imbalanced data, SMOTE, NearMiss. These imported libraries and modules are crucial for diverse tasks such as data preprocessing, model building, evaluation, visualization, and addressing imbalanced datasets. The warning suppression at the end helps prevent unnecessary warnings from cluttering the output. This code is fundamental for data scientists and machine learning practitioners to effectively work on different aspects of developing and evaluating machine learning models. This script loads the creditcard.csv file into a pandas dataframe by utilizing the read_csv function from the pandas library. The file path provided, /input/creditcard.csv, is a relative path indicating the file's location within the directory structure. Upon loading the file into the dataframe, df, the head method is applied to view the first few rows of the dataframe. This step assists in quickly examining the data's appearance and understanding its layout. Utilizing this script is significant as it facilitates the transformation of data from a CSV file into a format that is easily analyzable and editable using Pandas' robust functionalities. The head method aids in obtaining an initial overview of the dataframe's contents. This process computes the percentage of fraudulent and non-fraudulent transactions in a dataset. It begins by tallying the occurrences of each class, fraudulent and non-fraudulent, in the class column of a dataframe. Next, it determines the percentage of each class by dividing the count of each class by the total number of rows in the dataframe. This division result is then multiplied by 100 to yield the percentage, which is rounded to 2 decimal places for clarity. This approach is valuable for grasping the distribution of fraudulent and non-fraudulent transactions in a dataset. Understanding the percentage of each class in the dataset aids in recognizing any imbalances between the classes and guides the adoption of appropriate data preprocessing or modeling strategies, particularly in scenarios like fraud detection tasks where the amount of fraudulent transactions is typically significantly lower than non-fraudulent ones. This text explains how to use the Seaborn library to create a count plot for visualizing the distribution of classes in a dataset named df. The countPlot function from Seaborn is utilized to aggregate and display the occurrences of each class as bars on the plot. To create the countPlot, the line of code SNS countPlot class data equals df palette equals colors is used, specifying the class column from the df dataset for plotting the counts. A custom color palette colors is provided to assign different colors to each class for easier differentiation on the plot. Additionally, the code includes plt title, class distributions, n, 0. No fraud, 1. Fraud, font size equals 14. To add a title to the plot indicating the represented classes, 0 and 1. The title is placed at the top of the plot with a font size of 14 to enhance readability. This code is beneficial for visualizing class distribution in datasets like fraud detection, where understanding the balance or imbalance of class distribution is crucial. The countPlot offers a clear visual representation of class distribution, facilitating data analysis and interpretation. Customizing the plot with colors and a title improves clarity and enhances understanding of the presented information. This snippet produces a figure with two subplots placed beside each other. The first subplot displays the distribution of transaction amounts using a Seaborn distplot in red, while the second subplot shows the distribution of transaction times using a Seaborn distplot in blue. Adding titles and adjusting the x-axis limits for both subplots enhances clarity and aids in understanding the visualized data. This code segment is valuable for examining the distributions of transaction amounts and times within a Pandas dataframe through Matplotlib and Seaborn. By visualizing these distributions, one can gather insights into the spread and frequency of various values in the dataset, which is beneficial for exploring and analyzing data in fields such as finance, fraud detection, or other domains involving transaction records. This text refers to a Python script that uses standard scalar and robust scalar classes from scikit-learn's preprocessing module to standardize numerical features in a data frame. The process involves creating instances of standard scalar and robust scalar for standardizing numerical features. It then utilizes robust scalar to transform the amount and time columns in the data frame, creating new columns, scaled_amount, and scaled_time, with standardized values. Finally, the original time and amount columns are dropped from the data frame. Standardizing features is crucial in machine learning to ensure all features are on the same scale. It helps algorithms converge faster, prevents dominance of features with larger scales, and enhances overall model performance. The standard scalar and robust scalar classes from scikit-learn are commonly used for this purpose. This process involves working with a data frame named df. It initially saves the columns, scaled_amount, and scaled_time, from the data frame into separate variables. Afterward, it removes these two columns from the data frame using the drop function. Next, it reinserts the scaled_amount and scaled_time columns back into the data frame at the beginning, index positions 0 and 1 foot, using the insert function. By following these steps, the code rearranges the columns in the data frame by placing scaled_amount and scaled_time at the front. Such restructuring can be useful when these columns are vital for analysis or visualization and need to be easily accessible at the beginning. In summary, this code snippet alters the column order in the data frame by prioritizing specific columns at the front. This process is responsible for dividing the data into training and testing sets while keeping the target class ratio consistent in both sets. Initially, it displays the percentage of each class in the dataset and separates the features, x, from the target variable, y. The code utilizes stratified k-fold to split the data into 5 folds, maintaining class proportions in each fold. It then shows the indices of the training and testing sets for each fold. Once the splits are completed, the training and testing sets are converted back to numpy arrays. The code subsequently displays the label distributions in the training and testing sets to verify that the ratio is preserved. This approach is critical as maintaining class balance in both the training and testing data is vital for unbiased model performance evaluation. By leveraging stratified k-fold, it guarantees that each fold mirrors the class distribution of the entire dataset, which enhances evaluation accuracy and model generalization. This text describes data preprocessing steps performed on a dataframe likely containing credit card transaction data with a class column denoting fraudulent or non-fraudulent transactions, 1 for fraud, 0 for non-fraud. The steps are: 1. The original dataframe, df, is shuffled randomly using the sample method with frac equals 1 foot to randomize all rows. 2. Two new dataframes are created. Fraud_df contains rows with class equal to 1 fraudulent transactions. Non_fraud_df includes 492 randomly chosen rows with class equal to 0 non-fraudulent transactions to balance the dataset, since fraudulent transactions are usually outnumbered by non-fraudulent ones. 3. The fraud_df and non_fraud_df dataframes are combined into a new dataframe named normal_distributed_df. 4. Normal_distributed_df is shuffled again using the sample method with parameters frac equals 1 foot and random_state equals 42 feet for reproducibility through consistent shuffling. 5. Lastly, the initial rows of the shuffled new_df dataframe are displayed. This approach is employed to handle imbalanced datasets where one class, here, fraudulent transactions, is significantly less represented than the other. Balancing the classes aids in training machine learning models effectively to prevent bias towards the majority class. Additionally, random shuffling eliminates any inherent order in the dataset that might impact the model's performance. This snippet generates a visual representation of the distribution of classes in a subsample dataset. Here's an overview of its functionality. 1. Printing class distribution **. It displays a message announcing the distribution of classes in the subsample dataset. It calculates the percentage distribution of each class in the class column of the new_df dataframe. This calculation involves counting the occurrences of each class and dividing that count by the total number of entries in the dataframe. 2. Plotting the distribution * utilizes SNS countplot from the Seaborn library to create a count plot of the class column in the new_df dataframe. The color palette for the plot is specified in the palette argument. The plot's title is set using plt title. Finally, plt show is used to display the count plot. 3. Purpose *. This code facilitates visualizing the distribution of classes in a classification dataset. Understanding class distribution is vital in tasks like classification to detect any class imbalances that could impact the model's performance. By visualizing the distribution, it is possible to determine if the classes are evenly distributed or if there is a significant class imbalance requiring specific modeling techniques or data preprocessing strategies. This figure shows two subplots arranged vertically, each displaying a heat map of the correlation matrix of two datasets, df and new_df. These matrices illustrate the relationships between variables in the datasets. In the first subplot, AX1, the correlation matrix of the original dataset, df, is plotted using the cool_warm_r palette to represent correlations with cool to warm colors. Correlation values are annotated with a font size of 20. And the subplot is titled, Imbalanced Correlation Matrix, with a font size of 14. The second subplot, AX2, displays the correlation matrix of a subsampled dataset, new_df, using the same, cool_warm_r color map, correlation annotations, font size, and title styling, subsample correlation matrix, with a font size of 14, as the first subplot. This code aims to visualize the correlation structures within datasets and compare them between the original and subsampled data. Heat maps of correlation matrices are useful for identifying patterns and relationships between variables, which is essential for data analysis, feature selection, and modeling. The use of different color maps and styles enhances the interpretability and informativeness of the visualizations. This script generates a figure with 4 horizontally arranged subplots. Each subplot contains a boxplot displaying the distribution of a specific feature, V17, V14, V12, V10, based on the target variable class. The boxplots are created using Seaborn's boxplot function. The palette parameter adjusts the colors of the boxplot elements, and the ax parameter designates the axes where each plot will be displayed. The set_title function assigns a title to each subplot. This approach is beneficial for examining the relationship between the chosen features and the target variable in a concise and structured manner. By visualizing the boxplots side by side, it facilitates comparing the distributions and identifying any notable differences between the classes. This can aid in exploratory data analysis and gaining insights into the data prior to utilizing machine learning models. This procedure generates a figure containing 4 subplots in a row, each exhibiting a boxplot. The boxplots illustrate the connection between various features, V11, V4, V2, V19, and the target variable, class. Every subplot is produced using the Seaborn's SNS boxplot function, with X denoting the target variable, class, Y representing the analyzed feature, data as the dataframe with the data, palette specifying the colors to use, and ax assigning the subplot for the boxplot. Subsequently, each subplot is given a title to offer context on the displayed information. Finally, PLT show is used to exhibit all the subplots at once. This method is valuable for visualizing the feature distribution in the dataset concerning the target variable. Boxplots are beneficial for detecting patterns, outliers, or correlations between features and target variables, particularly in binary classification scenarios like fraud detection, where the class variable typically denotes the presence or absence of fraud. This text describes a data visualization process using the Seaborn library to explore the distribution of three features, V14, V12, and V10, in fraudulent transactions. The breakdown includes importing the norm object from SciPy stats, creating subplots for each feature, extracting feature values, plotting histograms with normal distribution curves, applying colors for distinction, adding subplot titles, and displaying the plots side by side. Analyzing the distribution of features in fraudulent transactions helps in identifying differences from non-fraudulent transactions, which is valuable for fraud detection, anomaly detection, and data analysis. This code snippet is essential for data exploration and understanding data distribution in data analysis tasks. This procedure is designed to identify and eliminate outliers from specific features within a dataset relevant to fraud cases. Initially, the interquartile range, IQR, is computed for each feature, V14, V12, and V10, by employing the 25th and 75th percentiles. Subsequently, lower and upper bounds for outliers are determined based on the IQR. Any data points that fall outside of these boundaries are recognized as outliers and aggregated into a list. Following the identification of outliers, the procedure proceeds to remove them from the dataset for each feature. The elimination of outliers aids in cleansing the dataset and enhancing the accuracy of machine learning models or statistical analyses. This step is particularly critical in scenarios such as fraud detection or anomaly detection, where outliers have the potential to distort results and adversely impact model performance. This script generates a figure with three subplots side by side using the matplotlib and Seaborn libraries in Python. Each subplot displays a boxplot representing the distribution of a particular feature, V14, V12, V10 inches, based on the class variable in the new_df dataset. The boxplots are color-coded using two distinct colors, #B3F9C5, #F9C5B3, to distinguish between the classes, aiding in visually comparing feature distributions. Annotations are included in each subplot to indicate a reduction in extreme outliers in the feature distribution post-outlier reduction. These annotations are positioned at specific coordinates with arrows pointing to relevant positions on the plot. The figsize parameter in PLT subplots determines the size of the displayed figure. This code is beneficial for exploring and visualizing feature distributions in a dataset, particularly when comparing distributions across different classes or groups. Boxplots are effective for visualizing data distributions and spotting outliers, while annotations offer supplementary information or insights in the visualization. Dimensionality reduction is a common practice in machine learning and data visualization to streamline datasets by reducing the number of features while maintaining essential information. This aids in enhancing processing speed, minimizing noise, and uncovering patterns or clusters within the data. This process was applied on dataset X using three methods: TSNE, T-distributed stochastic neighbor embedding, PCA, principal component analysis, and truncated SVD, singular value decomposition. Each technique produced a two-dimensional representation of the data. The efficiency of each method was evaluated by measuring the time taken for dimensionality reduction using the Python time module. By assessing the elapsed time for each technique, one can better discern the computational efficiency of the methods and select the most appropriate one according to the task's requirements. This figure displays 3 subplots arranged horizontally, each showcasing data clusters using various dimensionality reduction methods TSNE, PCA, and truncated SVD. In each subplot, scatter plots illustrate data points in a reduced feature space, with different colors denoting fraud, red, and no fraud, blue, samples. The subplot titles specify the dimensionality reduction technique applied. Furthermore, the custom legend labels, no fraud and fraud, with respective colors, blue and red, aid in easy identification. The blue underscore patch and red underscore patch variables define the colors used for the legend labels. This code is beneficial for visualizing high-dimensional data in reduced dimensions, enabling the identification of patterns or groupings in complex datasets. Dimensionality reduction techniques simplify data visualization while preserving vital information. The legend enhances interpretation by providing a clear color code for different classes. The given data frame, new_df, is separated into 2 parts: features, x, and target variable, y. The x data frame consists of all columns from new_df except the class column, isolating the features used for predictions. The y series contains only the class column from new_df, representing the target variable for the machine learning model predictions. This separation of data into features and target variable is a crucial step in machine learning tasks, enabling proper training and evaluation of the model with the correct inputs and outputs. This snippet uses the train_test_split function from the sklearn model_selection module in the scikit-learn library. It aims to divide the dataset into training and testing sets. Here's a breakdown. X represents the input features data, independent variables, and Y represents the target data, dependent variable. The function creates 2 sets: x_train for training input features and x_test for testing input features. Similarly, y_train and y_test store the target values for training and testing. The test_size parameter determines the percentage of data allocated to the test set. For example, with test_size equals 0.2, 20% is for testing, and 80% is for training. The random_state parameter controls the shuffling of data before splitting. Setting random_state equals 42 ensures reproducible random splits. This practice is common in machine learning workflows to train a model on one data subset and evaluate its performance on another unseen subset. This verification helps gauge the model's generalization to new data and guards against overfitting. This process converts the training and testing data sets, x_train, x_test, y_train, y_test, from pandas dataframes to numpy arrays. This conversion may be required as certain machine learning libraries, like scikit-learn, primarily operate with numpy arrays rather than pandas dataframes. By transforming the data into numpy arrays, we guarantee compatibility with these libraries and can smoothly execute machine learning tasks. This text describes the creation of a dictionary named classifiers with 4 key value pairs. Each key represents the name of a classification algorithm, e.g., logistic regression, k-nearest, support vector classifier, decision tree classifier, and each value corresponds to an instance of the corresponding classifier class, e.g., logistic regression, k-neighbors classifier, SVC, decision tree classifier. The purpose of this dictionary is to provide easy access to instances of different classifiers based on their names. This approach simplifies the comparison and testing of various classifiers in machine learning experiments by allowing direct reference to the classifier's name instead of creating each instance separately. In summary, this dictionary streamlines the process of accessing and utilizing different classifiers in machine learning tasks by organizing them for efficient reference and utilization. This snippet evaluates the performance of different classifiers using the cross_val_score function from the scikit-learn library. It starts by importing the necessary function from scikit-learn and then iterates over a dictionary of classifiers to fit each one on the training data x_train and y_train. For each classifier, it computes the cross-validated accuracy score using 5-fold cross-validation, CV = 5. The cross_val_score function fits the classifier, conducts cross-validation, and provides accuracy scores for each fold. It then calculates the mean accuracy score across all folds. Finally, the code displays the classifier's name and the mean accuracy score as a percentage for the training data. This code is helpful for evaluating and comparing different classifiers' performance on a dataset. Using cross-validation offers a more reliable estimate of the classifier's performance compared to a single train test split. The output assists in determining which classifier performs better on the training data. This snippet demonstrates how to utilize Grid Search CV from the scikit-learn library to tune hyperparameters for various machine learning models. Grid Search CV is a technique used to find the best hyperparameters of a model by evaluating models with different hyperparameter combinations. In this example, the code searches for optimal hyperparameters for classification models such as logistic regression, k-nearest neighbors, support vector machine, and decision tree classifiers. The code first defines dictionaries with different hyperparameter values for each model. Then, Grid Search CV is employed to determine the best hyperparameters by fitting the model to the training data. After running Grid Search CV for each model, the best performing model is chosen from each group using the best_estimator_ attribute to retrieve the best model with the tuned hyperparameters. Hyperparameter tuning enhances the performance of machine learning models by finding the best parameter set that improves accuracy or other evaluation metrics based on the input data. This text describes a machine learning workflow that includes model evaluation using cross-validation. The process involves computing cross-validation scores for different classifiers, logistic regression, k-nearest neighbors, support vector classifier, and decision tree classifier, using the cross_val_score function. Cross-validation is a resampling technique used to assess machine learning models on a limited data sample more robustly than simple data splitting. The code snippet calculates the average cross-validation score over 5 folds, CV = 5, for each classifier, representing their performance on unseen data. The results are then printed in a human-readable format for evaluation and comparison. Overall, this code is crucial for evaluating and contrasting the performance of various classifiers on the dataset. Through cross-validation, it offers a more accurate and dependable estimation of how well these models generalize to new data. This text discusses the process of implementing undersampling on an imbalanced dataset using the NearMiss algorithm. First, the dataset is divided into features, undersample_x, and the target variable, undersample_y. The data is then split into training and testing sets using stratified shuffle split, SSS. NearMiss algorithm is applied to undersample the majority class and create a balanced dataset. A machine learning pipeline combining NearMiss and logistic regression is used to train the model on the undersampled data. Model performance is evaluated using metrics such as accuracy, precision, recall, F1 score, and AUC on the original training data. Undersampling is a technique to address imbalanced datasets by reducing instances in the majority class to match the minority class. This helps the model learn from both classes equally and enhance prediction performance. NearMiss algorithm selects samples from the majority class close to the minority class, emphasizing difficult instances for classification. This function generates learning curves for 4 different machine learning models to visualize how the performance of each model changes as the training size increases. 1. Input parameters include 4 machine learning estimators: data, x, target values, y, and optional parameters like plot limits, cross-validation strategies, and number of parallel jobs. 2. The function creates subplots for each model and iterates over each model. 3. For each model, it generates a learning curve using the learning_curve function from scikit-learn, which calculates training and test scores for various training sizes. 4. Mean and standard deviation of scores for each training size are calculated. 5. The learning curve is plotted with shaded areas representing the standard deviation around the mean scores. 6. Each subplot contains the model name, axis labels, and a legend. 7. The function returns the plot. This function is useful for comparing model performance, diagnosing bias or variance issues, and guiding decisions on data collection or model selection. The learning curve visualization provides insights into the learning behavior of machine learning models. This analysis is conducting a learning curve assessment on various machine learning models using the provided training data in order to compare and evaluate their performance. The following components are involved. 1. Shuffle split asterisk. This function generates multiple random splits of the dataset for cross-validation. It creates 100 splits with a test size of 20% and a fixed random state. 2. Plot_learning_curve asterisk. This is a custom function used to plot the learning curve for the machine learning models. It displays how the models perform as the training set size increases, aiding in assessing bias and variance issues. 3. Models asterisk. The models under evaluation are log_reg, k-nears_neighbors, SVC, and tree_CLF. 4. Data asterisk. X_train and Y_train represent the training features and labels used for model training. 5. Evaluation asterisk. The learning curves are plotted within the performance range of 0.87, 1.01. 6. Cross-validation and parallelization asterisk. The learning curves are calculated using shuffle-split cross-validation technique and parallel computation with n_jobs equals 4 for faster processing of multiple models. In essence, this code snippet is crucial for evaluating the performance of machine learning models by analyzing learning curves. By observing model behaviors with increasing training data, it helps in identifying problems like overfitting and underfitting, aiding in making informed decisions about model selection and tuning. This text describes the process of generating predictions for multiple machine learning models using cross-validation. Logistic Regression and Support Vector Classifier use the decision function method to obtain predictions with confidence scores. K-nearest neighbors and Decision Tree Classifier use default methods to obtain class predictions. The purpose of using cross_val_predict is to generate cross-validated predictions for each model, which can then be used to evaluate the models using metrics such as ROC curves. Cross-validation helps prevent overfitting and provides a more reliable estimate of the model's performance on unseen data. In summary, this approach facilitates evaluating multiple machine learning models by generating predictions through cross-validation, allowing for a comparison of their performance using various evaluation metrics. This text explains the process of calculating the ROC AUC, receiver operating characteristic area under the curve, score for various machine learning models' predictions. The ROC AUC score assesses a classification model's performance by determining the area under the ROC curve, which illustrates the true positive rate versus the false positive rate across different threshold settings. A higher ROC AUC score signifies superior model performance. In this scenario, 1. The ROC AUC score is computed for the logistic regression, k nearest neighbors, support vector classifier, and decision tree classifier models. 2. The ROC AUC score function requires the true target values, y_train, and the predicted values from each model as its input. 3. The resultant ROC AUC scores are displayed in the console. Comparing and analyzing ROC AUC scores for diverse models is crucial for selecting the most effective model for a specific classification task. This practice aids in gauging the model's capacity to discern between various classes and make informed decisions based on the evaluation metric. This process computes the receiver operating characteristic, ROC, curve and the area under the curve, AUC, score for 4 classifiers: logistic regression, k nearest neighbors, support vector machine, and decision tree. First, the ROC_curve function is utilized to determine the false positive rate, FPR, and true positive rate, TPR, for each classifier by comparing the ground truth labels y_train and the predictions. Subsequently, a function named graph_ROC_curve_multiple is created to display the ROC curve for all 4 classifiers on a single graph. This function uses matplotlib to generate a figure, plot the ROC curves, label the axes, draw the diagonal line, representing random guessing, and display the legend with AUC scores for each classifier. The main objective of this process is to visually contrast the performance of the classifiers using ROC curves, focusing on TPR and FPR. This comparison aids in determining which classifier is more suitable for the specific problem based on the AUC score. The visualization provided by the ROC curve facilitates selecting the optimal model by considering the trade-off between TPR and FPR. The logistic_ROC_curve function is defined to plot a ROC curve for logistic regression using matplotlib. The ROC curve shows the true positive rate against the false positive rate at various threshold settings. It is a common way to evaluate binary classification models like logistic regression. The function plots the logistic regression ROC curve in blue and a red diagonal line for a random classifier. It also adds axis labels, limits, and a title to the plot. After defining the function, specific logistic false positive rate, log_FPR, and logistic true positive rate, log_TPR, values are passed to it, and the plot is displayed using PLT show. This code is helpful for visually assessing the performance of a logistic regression model in distinguishing between the 2 classes, true positive and false positive, at different thresholds. The ROC curve aids in understanding the trade-off between true positive rate and false positive rate, enabling the comparison of different models' performance. The scikit-learn library is utilized to calculate precision and recall values for plotting a precision recall curve. The precision_recall_curve function requires true target values, y_train, and predicted probabilities from a classifier, log_reg_pred, to compute precision, recall, and threshold values. Precision and recall serve as crucial evaluation metrics for binary classification tasks, particularly in cases of class imbalance. Precision gauges the correctly predicted positive examples relative to all examples predicted as positive, while recall quantifies the correctly predicted positive examples relative to all actual positive examples. The precision recall curve allows visualization and assessment of the trade-off between these metrics. The precision recall curve proves valuable for balancing precision and recall, particularly amidst class imbalances in datasets. It presents an extensive view of the classifier's performance across diverse probability thresholds, providing insights into the model's behavior under various circumstances. The curve assists in determining the suitable threshold based on the problem-specific needs. This text describes a process to calculate evaluation metrics for a logistic regression model. These metrics, recall score, precision score, F1 score, and accuracy score, are computed both on the training data to check for overfitting and on predictions from an undersampled dataset. The goal is to evaluate the model's performance using different aspects like recall, precision, F1 score, and accuracy. Comparing these metrics between the original and undersampled datasets helps assess the model's generalization and robustness against overfitting. Proper evaluation is crucial for identifying the model's strengths and weaknesses and determining any necessary improvements for optimal performance. This text explains a procedure involving a logistic regression model, log_reg, and testing data, original_xtest. The decision scores from the model are stored in the undersample_y_score variable. The decision_function method in scikit-learn calculates the signed distance of samples to the hyperplane. This distance can serve as a confidence score for the sample belonging to the positive class. In classification tasks, decision functions can help interpret the model's prediction confidence. Analyzing these scores allows decisions to be made based not just on predicted labels but also on the model's certainty level regarding those predictions. This analysis is beneficial in situations where the confidence in predictions is crucial. Utilizing decision functions offers additional insights into the model's predictions, aiding in decision-making and comprehension of the model's behavior. This snippet calculates the average precision score between predicted probabilities, undersample_y_score, and actual target values, original_y test, using the average_precision_score function from the sklearn library. Average precision score is a metric that evaluates binary classification models by considering both precision and recall. After the calculation, the code prints the average precision score rounded to 2 decimal places using a formatted print statement. Evaluating the performance of a binary classification model, especially with imbalanced datasets, and analyzing the precision recall trade-off is crucial. The average precision score helps in understanding how well the model identifies positive samples accurately while reducing false positives. This text discusses the process of analyzing a machine learning model's performance through the precision recall curve without including code details. The precision_recall_curve function from scikit-learn calculates precision and recall values based on model predictions and actual labels. The PLT figure function creates a new figure for plotting. The precision recall curve is plotted using PLT step to connect points and PLT fill underscore between to color the area under the curve. The x-axis represents recall, while the y-axis represents precision. The plot is labeled and formatted with appropriate limits and titles. Visualizing the precision recall curve is crucial for evaluating a model, especially in imbalanced datasets where accuracy may be misleading. Precision and recall provide additional insights into a model's performance, particularly in binary classification with class imbalances. The precision recall curve and metrics such as average precision assist in measuring the model's ability to identify true positives while reducing false positives. This explanation demonstrates the utilization of synthetic minority oversampling technique, SMOTE, in combination with logistic regression to address imbalanced datasets in a binary classification scenario. Here's an overview of the process and its significance. 1. Firstly, the code imports essential libraries, sets up the logistic regression classifier, and defines its hyperparameters for randomized search. 2. It then verifies the sizes of the original training and test sets to detect data imbalances. 3. The key section involves a for loop where stratified k-fold is used for cross-validation of the training data. SMOTE is implemented via imbalanced _make_ pipeline within the cross-validation loop, ensuring separate application on each fold to prevent data leakage. 4. After applying SMOTE on the training folds, the model is trained using logistic regression with hyperparameters optimized using randomized search and cross-validation. 5. The code calculates evaluation metrics, accuracy, precision, recall, F1 score, and AUC, to assess the model's performance on the test set. 6. Lastly, the code presents the mean values of these evaluation metrics across all folds. This code is essential for managing imbalanced datasets by oversampling the minority class through SMOTE. This process helps prevent bias towards the majority class, improving model generalization and overall performance metrics, particularly in classification tasks involving imbalanced datasets. This snippet evaluates the performance of a machine learning model trained to detect fraud using the SMOTE technique. The steps performed by the code are: 1. Define labels, no fraud, and fraud for the classification report. 2. Make predictions on the test dataset, original _X test, using a trained machine learning model, best _est, with the SMOTE method. 3. Compare actual target values, original _Y test, with predicted values, SMOTE _prediction, and generate a classification report. 4. The classification report includes metrics like precision, recall, F1 score, and support for both no fraud and fraud classes. The aim is to assess the model's performance in predicting fraud and non-fraud cases. The classification report summarizes the model's performance, aiding in evaluating accuracy and effectiveness in fraud detection. It is crucial to use this code to evaluate the model's performance and identify areas for enhancement before deploying it in a real-world setting. This process calculates decision function scores, y_score, for a given test dataset original _X test using a trained machine learning model best _est. The decision function provides insight into the model's confidence when predicting the target variable for each sample in the test dataset. A higher decision function score indicates greater confidence in the prediction. The interpretation of this score may vary depending on the machine learning algorithm employed. By obtaining these decision function scores, decisions such as setting classification thresholds, ranking samples by confidence level, and evaluating the model's predictive accuracy can be informed. Utilizing this method is crucial for evaluating the model's performance, making informed decisions, and understanding how the model performs on new data. The average precision recall score is calculated using the average _precision _score function from the scikit-learn library. This score is a metric commonly used to evaluate classification models, particularly in cases of imbalanced classes. It quantifies the trade-off between precision and recall by calculating the area under the precision recall curve. This considers both precision, positive predictive value, and recall, true positive rate, of the model. In this snippet, the average _precision _score, original _y test, y _score function compares the actual test labels, original _y test, with the predicted scores from the classifier, y _score, to compute the average precision score. The code snippet outputs the average precision score with 2 decimal places, providing a summary of the model's performance in terms of precision and recall. This information is valuable for evaluating and comparing classification models, especially in situations where balancing precision and recall is crucial. The following text describes the process of creating a precision recall curve for evaluating a machine learning model's performance in classification tasks, particularly in cases of class imbalance. 1. It generates a figure with specified dimensions using the matplotlib libraries plt. Figure, fig size equals 12, 6. 2. Utilizes the precision_recall_ curve function to compute precision and recall values necessary for plotting the curve. 3. Plots the precision recall curve with plt. Step to display steps in the curve and plt. Fill _ between to shade the area under it. 4. Assigns recall and precision as labels for the x-axis and y-axis, respectively. 5. Sets limits on the y-axis and x-axis to maintain appropriate scaling of the plot. 6. Includes a title in the plot showing the average precision recall score obtained from the model, aiding in the interpretation of model performance. Creating a precision recall curve is crucial as it offers valuable insights into the classification model's efficacy across diverse thresholds. By visualizing the precision recall trade-off, informed decisions about model performance can be made, especially in scenarios with imbalanced datasets where accuracy alone may be deceptive. The SMOTE, synthetic minority oversampling technique, algorithm is utilized to address class imbalance in machine learning datasets. The process involves 1. Initialization of the SMOTE object with the parameter ratio equals minority, indicating oversampling of the minority class to equalize sample sizes with the majority class. 2. Utilization of the fit_sample method from the SMOTE object to create synthetic samples for the minority class in the training data, original_x_train and original_y_train, until the desired ratio is reached. SMOTE is essential when dealing with imbalanced datasets, where one class has considerably fewer samples than the other. This imbalance can introduce bias towards the majority class in the model. By generating synthetic samples for the minority class, SMOTE balances the class distribution, enhancing the model's performance, particularly in scenarios with skewed datasets. This procedure measures the time it takes to fit a logistic regression model on the oversampled training data. Here is an overview of the steps and their advantages. 1. Record the initial time before fitting the model to establish a reference point. 2. Assign the best logistic regression model, obtained from a grid search or similar process, to the variable log_reg_sm. 3. Fit the logistic regression model on the oversampled training data, xsm_train and ysm_train. 4. Record the time after the model has been fitted. 5. Calculate the duration of fitting the model by subtracting the start time from the end time and display it in seconds. Measuring the time taken to fit a model is essential for evaluating and optimizing performance. It helps in assessing the efficiency of the model training process, enabling comparisons between models and optimization of hyperparameters. This data provides insights into the computational resources required for training the model and aids in evaluating scalability, particularly with large datasets or intricate models. This text describes generating confusion matrices for multiple machine learning models and visualizing the results using heat maps. The steps involved are: 1. 4 machine learning models, log_reg_sm, kneighbors, svc, tree_clf, are used to make predictions on the test data, x_test. 2. Confusion matrices are calculated for each model by comparing the true labels, y_test, with the predicted labels. 3. A 2x2 grid of subplots is created using PLT subplots to display the confusion matrices for each model side by side. 4. The SNS heatmap function is used to create heatmap visualizations of each confusion matrix with annotated cell values. 5. The subplots are customized with titles displaying the model name and type of confusion matrix. Visualizing the confusion matrices allows insights into the performance of each model in predicting the target classes accurately. This visualization aids in understanding the strengths and weaknesses of each model, assisting in making informed decisions regarding model selection and improvements. This text discusses the evaluation of different machine learning models through the generation of a classification report for each model's predictions. The classification_report function from the sklearn metrics module is utilized to produce a text report that displays key classification metrics like precision, recall, F1 score, and support for each class. In each section, the code displays the model's name, e.g., Logistic Regression, k-neighbors, support vector classifier, followed by the classification report outlining the model's performance on the test data. This approach is crucial for assessing the effectiveness of machine learning models as it offers valuable insights into their ability to predict the target variable. By analyzing metrics such as precision and recall, we can identify the strengths and weaknesses of each model, enabling us to make informed decisions about selecting the most suitable model for a specific task. This text describes a process for calculating the accuracy scores of two classification models applied using different sampling techniques: random undersampling and oversampling, SMOTE. 1. The accuracy score for random undersampling is determined by comparing true labels y_test with predicted labels y_pred obtained from a logistic regression model log_reg. 2. The accuracy score for oversampling, SMOTE, is calculated by comparing true labels original_y test with predicted labels y_pred_sm from the best estimator model best_est. 3. The accuracy scores for both techniques are then stored in a dataframe named final_df with columns, technique, and score, to show the results and the techniques used. 4. Finally, the code reorders the columns in the dataframe so that the score column appears as the second column. The purpose of this code is to assess the performance of random undersampling and oversampling, SMOTE, in improving the accuracy of classification models. This evaluation helps in analyzing the efficiency of these techniques in handling imbalanced datasets and enhancing the overall model performance. This text discusses the use of the Keras library for building a neural network model. Here is a summary of the steps involved. 1. Import necessary modules from the Keras library, which is now integrated into TensorFlow. 2. Determine the number of input neurons based on the shape of the input data, x_train. 3. Create a sequential model which represents a linear stack of layers. 4. Add layers to the model using the sequential constructor. The first layer consists of dense neurons equal to the number of input neurons with ReLU activation function. The second layer consists of 32 neurons with ReLU activation. The output layer consists of 2 neurons with a softmax activation function, commonly used for multi-class classification. This code snippet simplifies the creation of a neural network structure with specified layers, neurons, and activation functions for each layer. Keras provides a more user-friendly approach to defining and configuring neural networks compared to directly using TensorFlow, enhancing the ease and intuitiveness of building deep learning models. Using the summary method on a machine learning model, like an undersampled model in this instance, will give an overview of the model's structure and parameters. It includes details such as the number of layers, parameters in each layer, activation functions, and other specific information about the model's design. This summary is valuable for promptly grasping the model's setup and architecture, which aids in debugging, optimizing, or comparing various models. It offers a brief insight into the model's elements and can be beneficial in identifying any problems with the model's configuration. The neural network model is compiled using the ADAM optimizer with a learning rate of 0.001. ADAM is known for its efficiency in training deep learning models. The loss function selected is sparse_categorical_crossentropy, commonly used for classification problems with integer target outputs. The code specifies the accuracy metric for evaluating the model's performance during training and testing. This metric measures the ratio of correctly predicted samples to the total number of samples. Compiling the model is a crucial step in preparing the neural network for training. It configures the model with the specified optimizer, loss function, and metrics to enable training on a given dataset. This process involves training an undersampling model on the training data. Undersampling is a method used in scenarios where the number of instances in one class is much lower than the others in imbalanced classification problems. The parameters used in the fitting function are as follows: x_train and y_train. Features and labels of the training data. Validation_split equals 0.2. 20% of the training data will be set aside for validation to assess the model's performance as it trains. Batch_size equals 25. Number of samples in each training batch. Epochs equals 20. How many times the model will be trained on the full dataset. Shuffle equals true. Data will be shuffled before each training epoch. Verbose equals 2. Level of detail in the training output, displaying a progress bar for each epoch. By implementing this approach, the undersampling model is applied to the training data to mitigate class imbalance concerns by reducing instances in the majority class. This strategy can enhance model performance and alleviate bias towards the dominant class during training. This text explains how a machine learning model, undersample_model, is used to make predictions on a dataset, original_xtest. The predict method is employed to generate these predictions. The predict method utilizes the input data, original_xtest, to produce predicted output values based on the model's parameters. The variable undersample_predictions is used to store these predicted values. In this scenario, the model is configured to predict in batches of 200 with batch_size equals 200, and the prediction operation is set to run silently with verbose equals 0, indicating that no output will be displayed during the process. This code snippet aids in evaluating a machine learning model's performance on new data, original_xtest. By comparing the predictions with the actual values, users can gauge the model's accuracy and effectiveness. This script utilizes the machine learning model undersample_model to predict classes on a dataset named original_xtest. The model makes predictions on batches of 200 data points at a time without showing progress updates. These predictions are generated for fraud detection purposes, specifically after undersampling the dataset to address class imbalance. Undersampling involves reducing the instances of the majority class, non-fraudulent transactions, to equal the number of instances in the minority class, fraudulent transactions. This balancing allows the model to learn effectively with fair representation from both classes. The predicted outcomes can be utilized for subsequent analysis, evaluation, or decision-making in fraud detection tasks. The function plot_confusion_matrix generates a visual representation of a confusion matrix, which is a table describing the performance of a classification model based on true positive, true negative, false positive, and false negative predictions. The function accepts parameters such as the confusion matrix data as a numpy array, a list of class labels, a flag to indicate whether to normalize the data, the title of the plot, and the color map for the plot. It begins by checking if normalization is required and normalizes the matrix if specified. It then displays the matrix, plots it using matplotlib's imshow function with a chosen color map, sets the title, adds a color bar, assigns tick marks for classes, and labels the axes. The function determines the number format for displaying values, calculates the threshold for text coloring in the plot, iterates over the matrix to display values with adjusted text color based on the threshold. Lastly, it adjusts the layout, labels the axes, and creates the visualization of the confusion matrix. This function is helpful in visualizing the classification model's performance, highlighting correct and incorrect predictions to aid in model assessment and improvement. This text describes a machine learning project focused on evaluating the performance of a fraud detection model without the accompanying code. The process involves calculating and displaying the confusion matrix for two scenarios. 1. Random undersample. This scenario involves generating predictions using undersampled fraud data to evaluate the model's performance when trained on imbalanced datasets. 2. 100% accuracy confusion matrix. This scenario demonstrates perfect accuracy by comparing the model's predictions against the true labels to highlight ideal performance. The confusion matrix illustrates the model's predictive capabilities by showcasing true positives, true negatives, false positives, and false negatives. Visualizing the confusion matrices for both scenarios enables a direct comparison of the model's performance in various conditions. The plot_confusion_matrix function likely aids in visually representing the confusion matrices with color gradients to differentiate metrics like red for random undersample and green for 100% accuracy. This visualization helps in comprehending the model's effectiveness in identifying fraud and non-fraud cases. In essence, this text discusses evaluating and comparing the fraud detection model's efficiency under different conditions to assess its ability to detect fraudulent transactions effectively. This text describes the creation of a neural network model using the Keras framework within TensorFlow. The model consists of 3 layers, 2 hidden layers and 1 output layer. The first hidden layer matches the number of neurons with the input features in the training data. ReLU, rectified linear unit, is used as the activation function in the hidden layers to introduce non-linearity. The output layer contains two neurons with a softmax activation function, suited for multi-class classification tasks. Constructing neural networks in this manner allows for the specification of the model's architecture, such as the number of layers, neurons in each layer, and activation functions utilized. This architectural design plays a significant role in how the model learns and generates predictions. Leveraging deep learning frameworks like Keras simplifies this process, offering a user-friendly interface to define intricate neural network structures with minimal coding effort. This explanation is about configuring a machine learning model before training it. Here is a breakdown of what each aspect in this process does. 1. Oversample_model. Compile. This is a method call on a machine learning model named oversample_model. The compile method is used to configure the learning process by setting the optimizer, loss function, and metrics that the model will use during training. 2. Adam, LR equals 0.001. The optimizer is specified as Adam with a learning rate of 0.001. Adam is a popular optimization algorithm derived from stochastic gradient descent. The learning rate determines how much the model's weights are adjusted during training. 3. Loss equals sparse_categorical_crossentropy. This line defines the loss function to be used for training the model. Here it is set to sparse_categorical_crossentropy, which is commonly used for multi-class classification tasks with integer target variables. 4. Metrics equals accuracy. This line sets the evaluation metric for the model. Accuracy is chosen as the metric, which calculates the percentage of correct predictions made by the model. By using this line of code, the model is properly configured with an optimizer, loss function, and evaluation metric before training. This preparation step is essential for setting up the model for the training process and is a key aspect in developing machine learning models. Training a machine learning model using the fit method involves various parameters as explained below. 1. XSM_train. Input features for model training. 2. YSM_train. Target labels for model training. 3. Validation_split equals 0.2. 20% of the training data used for validation during training. 4. Batch_size equals 300. Number of samples in each training batch. 5. Epochs equals 20. Number of complete passes through the training dataset. 6. Shuffle equals true. Shuffling training data before each epoch to prevent memorization. 7. Verbose equals 2. Controls training verbosity, displaying one line per epoch. This approach is crucial for training models on imbalanced datasets using oversampling methods like SMOTE, synthetic minority oversampling technique. Oversampling the minority class can enhance the model's classification of underrepresented instances, reducing bias toward the majority class. Utilizing oversampling techniques during training can lead to improved model performance and generalization. This approach makes predictions using a model trained to address imbalanced datasets. It employs the predict method of the oversample_model to predict outcomes for the original _xtest test dataset. To break it down: 1. Oversample_model. Predict, original _xtest, batch_size equals 200, verbose equals 0. This line executes the predict method on the oversample_model object with the original _xtest test dataset as input. It creates predictions for the test data in batches of 200 to prevent excessive memory usage. The verbose equals 0 parameter ensures the prediction process is silent with no console output. This technique is beneficial in dealing with imbalanced datasets, where instances in different classes are unequally distributed. By utilizing a model tailored for handling such imbalances, such as oversample_model, the predictions generated are more trustworthy and precise compared to models that overlook class imbalances. This leads to enhanced performance metrics, especially for minority classes that are frequently underrepresented in the dataset. This snippet utilizes a machine learning model named oversample_model to predict outcomes on fresh data points known as original_x_test. To prevent memory problems, the model predicts on the test data in batches of 200 and uses verbose equals 0 to mute the output during prediction. The predict_classes operation is employed to acquire the predicted class labels for each data point in the test set. This is beneficial in classification scenarios where determining the predicted class for each data point is important. The code is used to assess the model's performance on unknown data, test data, by comparing the predicted classes with the actual ones to gauge metrics like accuracy, precision, recall, and others. By predicting outcomes with the test data, the model's ability to generalize to new, unseen data can be evaluated, potentially highlighting issues such as overfitting or underfitting. This text talks about creating and displaying confusion matrices for two different scenarios. 1. The first scenario involves a model named oversample, SMOTE. The confusion matrix compares the model's predictions with the actual values, original_y test, using the confusion_matrix function. This evaluation method is valuable for assessing predictive model performance, particularly in the presence of class imbalance and when techniques like SMOTE have been applied. The confusion matrix details true positives, true negatives, false positives, and false negatives. 2. The second scenario reflects a model with 100% accuracy, achieved by comparing the actual values with themselves. This theoretical scenario illustrates a confusion matrix for a perfectly accurate model. In summary, the code visually presents and contrasts the performance of a model trained with SMOTE oversampling against a scenario of perfect accuracy. It aids in understanding how the model categorizes different classes, no fraud, and fraud, and is pivotal for assessing the model's effectiveness in fraud detection and minimizing misclassifications.